means something changing in time. It's typical to take kind of early data and use that to predict later data. So we had something like that, and then we say train on this, test on that, and people say stuff like 80%, 20%. It's hard to know what's the best, but you're not going to get many people arguing who's used 80.
So if you decide to do cost validation and you want to train another model, so do you maintain the same split and then, or how do you split it for the second model?
So what we just did is we trained a parabola on the training set, and we trained a cubic on the training set. And then we used both of those to make predictions for the test set and computed their prediction errors for both of them. If I came back and said I want to fit fourth power, I would do it on the same training set and predict for the same test set, just to make it comparable. So if it's time series data, I usually try to respect the time aspect of it. If it's not time series data, so this would be something like a housing data set, or I've got my list of users and I know what they clicked on, and then I want to know, will they click on this new ad? And I ran a test and saw if they clicked on it or not. And then I want to say, well, what about the users helps predict whether they click on the new ad or not? I guess I collected the data over time, but time is not the main thing there, right? It's more about what have they shown interest in the past. So there's two ways to do it. One is called 50% holdout. Well, there's actually kind of three ways. There, you randomly pick 50% of your data, and that's the training set, and the rest of it is the test set. And you draw your models. Fit each model on the training set, and then make predictions for the test set and compute prediction errors. And then do you pick the best model? The model that does the best there? Well, how do you know that you picked the right 50%? I mean, you just did it randomly. So maybe try it again. Pick another 50%. So just forget whatever you had done there except to summarize. Just repeat that how many times? As much time as you have. And then you'll get a bunch of these summaries, and then after that, you can say, well, which one did the best on all of this training and predicting stuff. So that's one way to do it. Again, there's no particular reason to use 50%. You could use 80% and 20%. Another way to do it is called k-fold cross-validation. You might say, I'm going to take my data set and break it into, let's say, 5 blocks. Okay, it could be 5 or 10 or whatever. And you'll say, I'm going to use these 4 to predict this one. So these 4 are training, that one is next. And then you'll say, I'm going to use this one, not that one, this one, and that one to predict this one. And then, so you'll try every combination of use these 4 to predict this one. and then summarize all those. And then the last one is called leave one out. And that says instead of 50%, 50%, or 80%, 20%, make it all of my data except one data point, and then predict for that one data point. And then go try that for pretty much every data point. Keep repeating that, hopefully, if you have time, for all of your data points. There are times when that doesn't work so well, but they're kind of complicated. If you know stats, you might have heard of a jackknife method. So those are the main ways we avoid overfitting. Just keep training the model and then testing on stuff that we didn't train on. Any questions so far? So related to all of this is something called the Common Task Framework. And people have credited this for basically all of the advances we've made in machine learning and stuff in the last few decades. It used to be, someone would say, I'm going to make predictions from this thing and see how they go, and then they publish a paper. Someone else says, okay, well, I'm going to make my predictions, and no, look, I got better predictions. But they weren't doing cross-validation and stuff. So the way a lot of machine learning stuff happens now is someone publishes a data set, says train on this data set, and then they publish a test data set without the thing you're supposed to predict. So they publish training data and test data without the values to be predicted. You run your machine learning algorithm on the training data, you make predictions for the test data, and then you upload your answer, and they score it without revealing what the values were actually supposed to be. And train here, I should mention, you probably figured this out. It's like adjusting the coefficients in your linear regression model or on a neural network or something. And then the organizer of the competition scores your predictions. But just, they don't tell you each one, they just tell you overall, here is your sum of squared errors or something. And then often they maintain a leaderboard, and you can say, ooh, this other team did something better than us. Now we gotta go tweak things again and re-upload our predictions. So have you ever heard of competitions that do this? There's two big ones. They're not exactly the same class, but you heard of the Netflix challenge? Raise your hand if you've heard of the Netflix challenge. Really, only that many people. Okay. So there they gave a data set that was like a person ID number, some movie that they watched, and their rating of the movie, like 1 through 5. So they published that for, I don't know, 1 million people, or 1 million people movie combinations. And then the test data was some person ID number, movie ID number, and then blank. So Netflix knew what that blank was, but they're not telling you. And so you try to predict what their rating of that movie would be. Then you upload that data set, and they go check your predictions against what they know. And they say, okay, you're doing like 5% better than our current algorithms do. And the goal was to get 10% better than the current algorithms. And if anyone did that, the winner would get $1 million. And someone got like 10.001 and got the $1 million. And Netflix ended up not using that algorithm because by then stuff had changed. And also it wasn't just one person, it was a team of like, these 5 people were working as a team, and then these other 7 people were working as a team, and then they said, hey, let's combine, and then they combined with another team. So it ended up this big mess. But it was the first big kind of machine learning competition. That was like 5 years ago? I can't remember exactly. So the Netflix challenge is one. They're not doing that anymore. The other big place to do this is at Kaggle.com. They host a bunch of different competitions. They have one where they've got someone hooked up a bunch of dogs who are prone to epilepsy with like heart monitors and brain monitors, and recorded their heart and brain activity, and then they said, okay, well this dog, here's its record for an hour, and this is data sampled like 100 times a second. So here's an hour's worth of data, and then it did have a seizure. And then here's another dog, here's an hour's worth of data, this one did not have a seizure. So let's predict whether the dog will have a seizure or not based on its heart and brain function. So that's some pretty cool stuff, right? They've also done like oil exploration and cancer detection and all kinds of stuff. So they've done a good job publishing like simple data sets. You can kind of get started pretty easily, and then you can work your way up. Any questions on all that? So that data is usually on the kind of medium size. Like it might be a few hundred megabytes, but they don't usually get into like, you really need a Hadoop cluster to handle this. All right. What else do you want to say? Any questions so far? All right, so far we've been talking about regression, like predicting house values or something. Another thing we might want to do is predict yes or no things, so make classification answers. Okay, so we were doing that last time. So here we've got a set of patients and a team's prediction of whether that person would get cancer, like based on their gene activity or something, and then whether the person actually got cancer. And here's the same set of people, but another team's predictions. Or maybe it's really the same team, but just two different models. So, which team did better? Okay, so calculate validation error. This person did not get cancer. The team didn't say they wouldn't get cancer. They didn't say they will get cancer. They gave an answer somewhere between absolutely will and absolutely won't. So for the first person here, which team had a better prediction?
Second one.
The second. How about for the second person, which team had a better prediction?
Second one.
The second one. How about for the third person? Okay, it's looking pretty good for team 2 here. How about for the fourth one? Still the second one. How about for the fifth one?
First one.
Now team 1 did better. How about for the fifth one? Team 2 just a little better. So overall, it looks like team 1 did worse. But how can we quantify, put a number on it? Well, we could just say, for each, like we did for each one, who wins, this team or that team. But what if team 2 kept basically the same predictions? They won on almost every single person, right? But what if this number got a little higher and that one got a little lower? Then comparing them to team 1, you'd still have the same answers, right? Of who won each little competition. So one way you might think of doing this is to compute the residual, like subtract those two. But a better way to do it is to say, how likely was this given their prediction here? So that's called a likelihood. How likely was the observation? Assuming the prediction was good. So if someone says 0.01 chance of something happening and then it doesn't happen, that's a pretty good prediction, right? How likely is this based on that prediction? It's actually really likely to get a 0. So how likely is getting a 0 when the chance of getting a 0 is low? It's that. How likely is getting a 1 when the chance of getting a 1 is high? It's just the same number. How likely is getting a 0 when you got that number? It's 1 minus that, just like it was 2 rows above. Here, I can just copy that, and do 1 minus that. And then I want to boil those all down to one number. So what should I do with all of those? Well, we used to add squared residuals, but now it's actually better to multiply. Why is multiplying the right thing there? Because, yeah, we don't usually add probabilities. If I added those, I would get something above 1.0, which is a sign that something's gone wrong. But if I had a bunch of coins and I said, there's a 50% chance of heads on this one and a 50% chance of heads on this one, what's the chance of getting heads on both of them? You multiply the 50%. So that's why we're multiplying. So I can do this. So this team had a lower overall likelihood than that one, and we want the maximum likelihood. All right. So that's going to be our goal in doing yes, no kind of prediction. So here we didn't say how they got their predictions. They probably had gene activity levels or something. You'd say, let's put gene activity level this way and make a probability prediction this way. Would a linear function be good for that? I've got like this gene is very active, not so active, then a straight line. What's that straight line going to do? You go above 100% at some point and below 0% at some point, which is not good, right? So we need some kind of function that will stay between 0 and 1. Parabola? No, parabola is going to shoot to infinity this way or that way. Cubic, fourth power, exponential. Exponential is going to shoot off to infinity one way or the other. Okay, so we need a function that many people have not seen in their math training, and that's called the logistic function. It's this kind of S-shaped curve, and there's a nice formula for it. 1 plus 1 over e to the negative x. And here it's centered at 0, but we might want to move it so it predicts 50% maybe over here. And we might want it to be real steep, or we might want it to be not so steep, so we want to be able to stretch it this way. So I've got formulas in here. So it's 1 over 1 plus e to the something times x plus something else. So if I put a shift in here of like 4, then that curve shifted over and now it's centered at 4. It passes 50% at 4. So if I put a shift of -3, then it passes 50% at -3. Bring it back to about 1. If I change the scale, make it like, how about 6, then it's very steep. If I make it 0.1, then it's so unsteep it almost looks linear in this region. So I want to use this idea, take whatever x values I have, and put them through a function like this to give me a number between 0 and 1. So here's some data, some chemical or gene activity, and whether the person got cancer or not. And I want to put a shift and a scale in there to make my predictions turn out to be close to these data points in a likelihood kind of way. So what was that formula? 1 over 1 plus e to the minus scale times the x value minus shift. And here it's showing the predictions. Am I making good predictions? I am not missing a single case of cancer. Patient comes in, I say, you're going to get cancer. And no one gets passed without a prediction of cancer. That's pretty good, right? You don't like false alarms? I can fix that. How about we'll shift my logistic curve out to like 200. Now I'm predicting no one gets cancer. I have no false alarms. Maybe you want something in between. So we'll put the shift maybe around 60. Remember, I'm shifting it left and right. Okay, I'm predicting most people correctly, but not that one. And now I'm actually getting some results here. But notice most